is the homework assignment number 2. Number 2, part B. 11 questions. Originally, I want to post 12 questions, but after I make 11 questions, already 3 full pages. If 12, then the page number 4, and I feel it should be enough. 11 questions for practice, that should be enough. So I just stop after 11 questions. The first 7 questions, each one 4 points. So 4 times 7, 28 points. The last 4 questions, each one 5 points. So that's 20 points. 20 plus 28, total 48. Then I give you 2 more points. So the total 50 points. When I do grading, I use that way. Then together with part A, total 100 points. All right, so that's the homework assignment. Oh, and this week, after this one, this is the first one this week, I may need to give you 2 more assignments this week. Another one is quiz number 4. Because we just finished module 4. Today we start module 5. So we need to do a quiz for module 4. So that's one. Another one, project number 2. Project number 2, I will do official assignment on Wednesday's class. So Wednesday, I'll get everything ready. And I also show you a demo. To get you started, I give you the sample code to show you the demo to get it started. So that's the project number 2. And you have approximately 1 month to do it. So Wednesday plus approximately 1 month, even after final, you have a few more days. So I set deadline a few days after the final. Even after the final, you have a few days to complete the remaining work of project number 2. All right, so that's the assignment plan. Today, module 5, indexing and complex queries, 2 parts. Theoretical part, I want to explain the indexing technology. So this background, very important for you to understand DBMS, database management system. And sometimes you need to use it explicitly. So here, let me give you the background. So we will not go very deep for this topic. I just give you the basic understanding. We will not go very deep in this topic. But at the same time, another important topic we need to study in this module, complex queries. The query questions usually are much harder than our basic queries, module 4, basic queries. So we need to practice. So in homework assignment number 3, I may give you 11 or 12 questions, similar to homework assignment number 2, part B. So I will give you that many practice questions. So then, hopefully, you can build up some experience in SQL queries. All right, Part A, another student. Let me use this one to get, All right. Introduction to Indexing, 8.1. Why using indices? Yeah. Yeah. Let me explain the first question. Yeah. Why using indices? Yeah. And you also need to know what is the concept of indices. Yeah. So we will learn in this part. Yeah. The goal, speed up the retrieval of records in response to certain search conditions. Yeah. When we run select statement, retrieval, that's the typically we run our query select statement. Yeah. Sometimes if your queries are relatively complicated, the response time, the time you need to use, could be relatively slow. Yeah. Especially when you consider your database is very large. Yeah. Your table, your data, the data in your table, you have large number of rows. Yeah. Think about that. Yeah. Thousands of rows. Yeah. Thousands of rows we do not treat as very large. Yeah. Tens of thousands, hundreds of thousands, or millions, even millions of rows. That's possible. That's possible. Yeah. In that situation, how to make the data retrieval very fast? Yeah. So that's an important topic. Yeah. Yeah. All right. So in this module, we want to, look at the underlying algorithms. There must be some special algorithms inside DBMS to support, speed up technology, indexing. So that's that technology. Okay, speed up. Yeah. All right. Yeah. The idea very simple. Yeah. So when I explain the idea very simple. Okay. Yeah. Binary search. Yeah. Doing binary search, that could be much faster if you compare the linear search, right? Yeah. So here, at the beginning, at this point, I just give you the impression how fast we can improve the search performance, efficiency. You just consider linear search versus binary search. Yeah. Here, yeah. At the beginning, this point, how big is the improvement? Yeah. So I want you to connect. So these two search algorithms. The first one is the linear search or sequential search. Okay? Yeah. So given a table, when you need to find a specific row with certain given condition, you do linear search. You go through row by row, okay, iteration from the first row through the last row. That's the linear search, right? Yeah. And another way, binary search. Okay, versus, yeah. These two algorithm, you do comparison. Yeah. But the binary search, there is a requirement. Linear search, no requirement. You just do it. Okay? The binary search, yeah, data must be ordered. Must be ordered. But when you say ordered, you need to specify what kind of order, right? The order specifics, yeah, with respect to one particular column. Right? Yeah, because you have several columns. When you order your data, which column you want to use to sort all the rows in your table? Yeah. Yeah. You have several different ways, right? Yeah. So here, after you order your data based on one particular column, you can apply binary search. Then, how fast? Think about when you compare linear search, binary, how much is the difference? Now, linear search, if we use the algorithm asymptotic notation, that is big O of n, asymptotic notation, right? N, the number of data pieces, number of rows. But the binary search, we know you can improve that asymptotic notation to big O of log base 2 of n. Log base 2 of n. So that improvement is, is huge. That improvement is huge. Here, I just give you a simple example. Okay, here, if we use equals 2 to the 10th, that is 1024. This number, okay? Yeah. If we take log base 2 of n, we get 10. Linear search, with linear search, the worst case is 1024 linear search. And average case, so you may like to use average case to represent the overall efficiency, 1/2 of this number. 512, 1/2, 500 something, okay? All right. Yeah, so the binary search, the worst case efficiency here, 10, right? Yeah. Although you see the number 10, actually, to be more precise, actually it could be 11. Yeah. One more than that, 11. Yeah. But even 11, let's say the worst case 11, worst case 11, average case about 10. Here, average case 10. Yeah. Not exact 10, but close to 10. Yeah. Yeah. Worst case 11. Average is slightly more, a little more than 10. Yeah. Average case. Yeah. But that's the difference. Okay. Think about linear search, average case 512, worst case 1024. Okay? Binary search, average case about 10, worst case about 11. How much is the difference? That number of comparisons. Because when you do comparisons, that's the number of comparisons you need to do. That's huge improvement. Now you can see this simple technique. Just from linear search to binary search, you get a huge improvement. Okay? All right. So here, I just give you a simple description. But actually, in the real world DBMS inside implementation, the data structure is much more complicated. Yeah. So there is a sophisticated tree structure built inside the, supporting the indexing technology. Yeah. But for this class, I will not go that deep. Yeah. With that tree structure, the search improvement even much faster. Yeah. Even faster when you see the number here, 10, 11 here. Yeah. Yeah. even much faster. You can further improve. Yeah. For the data pieces, much more than 1,000 we see here. The data pieces we can handle million, billion, even billions in that level. Billions of data items, and the number of searches we will do, we improve to a very small number. That small number, let me give you an idea, 4 or 5. 4 or 5. Then to search a big table with billions of data pieces, when we use an advanced indexing technique, we just need 4 or 5 comparisons. So powerful. Why we can do that? Multi-level binary search. Yeah. The tree, when we build a tree, we build a sophisticated multi-level binary, because when you go from one level to next level, it's not a binary. Yeah. Why? The binary tree, when we go from one level to next level, the number of nodes doubled. Yeah. Then, if you use the multi-level search tree, it's not double. You multiply several hundred number. The branches, the number of branches in each level, several hundred branches. Then you can see how fast you can cover billions of data pieces. Yeah. Just the 4 or 5 levels, you can cover billions of data pieces. That's the reason you can do so fast. Okay? Yeah. But, for this class, I will not go that far. Yeah. You only need to know we can improve extremely well. Yeah, really, yeah. That number is so improvement, so huge. Yeah. Okay? All right. Yeah. So let me give you the basics, the detail here. Idea. The structure of the data is important for performance of data retrieval. Now, we need to do some special treatment. If you use the original table, you cannot do fast search. So you have to do some more work on top of the original table. But the one thing you need to make sure you cannot change the original data. Okay? Yeah. Otherwise, your business, you will get trouble. Okay? Yeah. So that's point. But the original structure of data should not be changed. Yeah. The reason is very simple, because you don't want to change the business specifics, right? Yeah. Because original data, it comes from your business requirements. Okay. So you don't want to change anything related to your business. Yeah. So your original table must be preserved. Okay? You cannot change anything on the original table. Okay? Yeah. But then the question is, if you are not allowed to change anything in the original table, how can you do the binary search? We know the original table is not ordered. Yeah, original table, the data, we collect the data in some random way, right? The random way. Yeah? Yeah. So you cannot assume there is any order. Yeah. In general, it's not ordered. Yeah. But if you're not allowed to change original table, how do you do the binary search? Right. So that the idea is very simple, but very smart. You use auxiliary tables. Yeah. You use auxiliary tables. Yeah. All right. So you preserve original table structure, but now you can add auxiliary tables, right? Yeah, that's extra data. That's the added data. Then you have freedom to use any specific structure on the original table, on the auxiliary tables. Yeah, that's the main idea. All right. Yeah. It may not support, yeah, definitely. Yeah. So if you apply the search on your original table directly, so most of the time you may not get good performance. Here, for large tables, not for small tables. For small tables, yeah, performance is good. So when we do our projects, usually the database very small, right? Yeah. Think about our company table. The largest table, the employee table, there are only 40 employees. Yeah. If you do sequential search, still very fast, right? Only 40 employees. Yeah. All right? Yeah. Yeah. But here, in the real world applications, we may need to consider some huge tables. Yeah. Then you really need to want to improve the search performance. Create auxiliary access structures. So we called this extra auxiliary access structure indexes. Indexes files. They are files. They are auxiliary tables. Each index, it's a file, auxiliary file, and it's also a table. Yeah. It is a table. Yeah. But this table is hidden. You cannot see it. Yeah. Nobody can see it. Okay? You create it inside DBMS. Yeah. After you create it, the DBMS will use those auxiliary tables to speed up the search performance. Yeah. But we do not need to do anything on it. Okay? We just set up. Okay? We tell DBMS, but we need to set up. Okay? So what kind of indices we want to define? Yeah. Yeah. So after you set it up, the DBMS will use it to speed up the search performance. That idea. Okay? All right. Based on the indexing field. Each index file, you need to specify an indexing field. Yeah? So I talk about when you sort the table, which column you want to use to do the sorting. So that column we call the indexing field. Yeah. All right. Yeah. Yeah. Here, multiple indexes on different fields for the same file are allowed. Okay? Yeah, multiple indexes. Yeah. Think about if I use the employee table, right? Yeah. So for example, in our employee table. Okay? Yeah. Many fields we can use to sort the data. Okay? For example, first name, F, we call it F name, last name, L name, right? Social Security number, SSN, right? Yeah. And other fields, okay? Yeah. The birthday, for example, B date, birthday, B day, and so on, okay? Yeah. So if you want, yeah. Yeah, because here, in this class, we do not need to create indexes. The reason only 40 columns. So, the gain, the benefit would not be big. 40, so that small number of rows, 40 rows. So you do not need to, that's overkill, right? You do not need indexes. Yeah. So it's not 4 million. 4 million, that large, huge number. Okay? Yeah, 40, only 40. 40, why we don't worry about searching a table with 40 rows because all the 40 rows are loaded into the main memory. All these 40 rows are loaded into the main memory. Then the linear search inside the main memory very fast. Yeah. So we don't worry. Yeah. So we don't need an index. Okay? Yeah. Right? Yeah. Yeah. But when you have huge amount of data, then you may not be able to load all your data into the main memory. Too much resource. Okay? No. You cannot use that much resource to hold that huge amount of data. Yeah. In that situation, indexing technology is very useful in that situation. Yeah, not here, okay? Not in the small database. Yeah. All right, so I will explain that point more later. Yeah. So here, just give you some basic information here. Yeah. All right. Yeah. So huge. Yeah, because then you have chance to use different indexing fields. So we call it different indexing fields. Yeah. All right. So multiple indexes for the same table. So you can set up, put there. And then the DBMS can choose, when do the binary search, can choose one of the auxiliary index files to speed up the search performance. Yeah. Okay. All right. Yeah. All right. Index basics. First, it's a secondary access paths, not primary access paths. Primary access paths corresponds to the original data. The business data stored in the original tables, that's the primary path, access path. Okay? Yeah. So when you store those original tables on hard drive, yeah. So hard drive, yeah. The permanent storage is in the hard drive. Yeah. Memory storage temporary, right? Yeah. The permanent storage is in the hard drive. Yeah. All right. Yeah. So you need to find, there is some specific way to access data on the hard drive. Okay, all right. Now here, the index files, they are secondary access path. They're auxiliary physical files. Yeah, physical, not virtual. So index files, they are all physical files. So they are physical files stored also on the hard drive. Yeah. Index files also stored on the hard drive. Yeah. Permanent. Yeah. Because although they are auxiliary files, but you want to use that part auxiliary data in a permanent way, not temporary way, the permanent way. Supporting your primary data all the time. Yeah, all the time. Okay? Yeah. Yeah. All right. So, but their access paths are different. Yeah. Quite different. Yeah. They have their own access paths. Yeah. All right? Yeah. Yeah. The mechanism to access the auxiliary files. Yeah. So additional files on disk. Yeah, that's the physical files, not the virtual files. Okay, all right. using extra storage space in exchange for better performance. So you need to use more hard disk storage space on the hard disk, hard drive, extra. But people don't worry about the extra storage space used because the cost of hard disk storage space per unit is very cheap, right? Very cheap. Yeah. So people are willing to spend that much money, extra, a little more money to make the search performance faster. Yeah. All right? Yeah. Okay. Sorting can be used in those additional files. Yeah. So those additional files, data, rows stored. Here I haven't talked about the specific structure of the indexing files. Yeah. So we will get there soon. Yeah, we will get there soon. Yeah. All right. Sorting. Yeah. Because though there are also rows, there are also tables, special tables, auxiliary files, also in the form of tables. So, and the data inside that table is sorted based on the indexing field. You have an indexing field. You have to declare an indexing field in order to create an index. Yeah. So then the rows in that auxiliary table must be sorted based on that indexing field. Okay. So you can apply the binary search. All right. Does not affect the physical placement of records in the primary data file on disk. So you do not touch, you do not change anything but on the primary data. Okay? Yeah. The business does not allow you to make any change on that. Okay? Yeah. Yeah. But there is a mapping. Yeah. Yeah. Because your auxiliary files, primary data files, how do you use auxiliary data files to get the data for the primary data files, right? Yeah. So you need to establish some connection, some mapping. Yeah. The mapping detail, we will see that detail later. Yeah. All right. Indexing fields. Basically, any field of the file can be used to create an index. Yeah. But basically, yeah, here it means 90-something%, but not 100%. There are some exceptions. There are some exceptions. You may not have this property. But 90-something% of the time, you can do in this way. Yeah. You can do it in this way. Yeah. Yeah. But that exception, those exceptional cases, yeah, so we also need to know a little bit. Yeah. Although the percentage very small, the cases, those cases very rare, yeah, but we need to know a little bit. Those small cases. Yeah. All right. Yeah, because though there are some cases, sometimes your table may contain the data, very special type of data. So that's possible. Yeah. So not necessarily those fields with total ordering. Yeah. Yeah. So here I'm talking about total order concept. Yeah. I remember I mentioned that total order concept before. Total order and a partial order. So here, there is a concept. Total order concept and a partial order concept. in our daily life, we're familiar with the total order. So what do you mean total order? Any two pieces of data, so if the domain has the total order property, then any pieces of data in this domain, you can do comparison. For example, numerical data, string data, dates, the dates, you can do comparisons, any two data items you can compare, you can order. That's the total order, yeah. But there is some special case called a partial order. Sometimes when you get two data items, you may not be able to find which one is larger, which one is small. You may have that special situation, although it's very rare, yeah, but that's possible. Okay, that's possible. Now, for example, here I just want to give you a simple example. Yeah. Basis, we can store binary data, right? Yeah. Remember multimedia data. Remember, we can store multimedia data directly in DBMS, right? Yeah, directly, not indirectly, okay? Directly in DBMS. And they are in the binary format, right? Yeah, the binary format, yeah. But the binary format, we know that could be very complicated, right? Yeah. Two binary files, the content, if we look at the content, the binary content could be very complicated. How can you define an order, right? The order, it's hard to define, okay? How do you define a certain order, right? Yeah. So you can see in some rare situations, you may not be able to define total order, yeah, or even order, even partial order, you cannot define, right? How can you define partial order? Yeah, even, right? Yeah, because the partial order, when you define partial order, you need to have the transitivity property. How to get a partial order? Because partial order is an order, right? Partial order is still an order. So the basic property it must have is, it must have the transitivity property. Transitivity property, okay? Yeah. So that means if A greater than B and B greater than C, then it must imply A greater than C, transitivity property, okay? So partial order, yeah. You must. Yeah, here, another example to show you why sometimes partial order exists in the real world objects. Yeah. So here I can, write another special example. Yeah. A, B, C, D, this is a graph, directed graph. Yeah. Directed graph. There is direction, okay? We can define A greater than B if there is an edge. Arrow, the edge is from A to B. If there is an edge from A to B, we say A greater than B. If there is an edge from B to D, then we say B greater than D. Because there is an edge from A to C, so we have A greater than C. There is an edge from C to D, we say C greater than D. Okay? So that's a special way to define an order. But this order is partial order. Okay? This order is not total order. So it's a partial order. Okay? Partial order. Why partial order? You can see when you pick B and C, can you compare B and C? Which one is larger, which one smaller? No. Because there is no edge from B to C, and there is no edge from C to D. So we do not know between B and C nodes, which one is larger, which one is smaller. No. There is no order comparison. Okay? So this is a partial order. It's not a total order. Yeah. All right. Yeah. So here, not necessarily those fields with total ordering. Yeah. Total. So here it says even your data does not have the total ordering, total order defined, you can still create indexing file for it. Yeah. But you cannot do binary search. If there is no total order, how can you do binary search, right? You cannot do binary search, but we use another technique. Because sometimes we cannot use binary search, then we use hashing. Hashing technique. Yeah. Hashing technique. Another special search algorithm. We know hashing is another very fast searching algorithm, right? Hashing. Okay? Yeah. Using hashing, we can do fast search. Yeah. But we do not need to do comparisons. Yeah. Hashing, we do not need to compare which one larger, which one smaller. We do comparison for a match. Yeah. In hashing technique, when we do comparison, we compare for a match. Match means if two data pieces, if they are exactly the same. But we do not need to know which one larger, which one smaller. We just want to know if two pieces of data, they are the same or not. That's enough for hashing. Yeah. Hashing technique. Yeah. Yeah. So that kind of comparison. Yeah. But in hashing, one item is bigger than the other, it's not important. That information is not important in hashing. Okay? Yeah. So if you have some algorithm background, so then you can use your algorithm knowledge. Algorithm, we will cover basic hashing a little bit. Yeah. You can use that knowledge to understand, another type of indexing files based on hashing. Yeah. All right. So we will talk about that later. Yeah. But the main part of the indexing file, that's the binary search based. Yeah. Hashing based on a very small portion. Okay. So if you cannot do the binary search, then you consider using the hashing technique. Yeah. All right. Some indexes do not use sorting. Yeah. So that's the, because there is no total order, how can you do the sorting? Yeah. But you still have a chance to do the, fast search based on the hashing technique. Yeah. All right. 8.2, data structures for indexing. Yeah. All right. Yeah. Order the files. Yeah. First, for order the files, it's simple. Yeah. Require total ordering. In order to do the sorting, you need total order. You have to sort the data for order, yeah, not just for matching, for ordering, yeah, not for matching, yeah. Matching, you don't need which one greater, which one smaller, just same or not same. So when you do comparison, you only want to know if the two given data pieces are the same or not same. That's for matching, search for matching. Another is search for ordering. Yeah. The two given pieces of data, which one is larger, which one is smaller? You want to know that. Okay? Search for ordering. Yeah. Yeah. All right. Use the binary search. Yeah. When you have order information, you can do binary search. Yeah. All right. Yeah. But here, there is one question I may like to point it out. Yeah. Because if some have a little bit algorithm background, yeah, so here. In algorithm, yeah, remember in algorithm, we have three basic search algorithm. Three basic search algorithm. The first one is linear search. Oh, sorry, linear search. Yeah. Or sequential search. Second is the binary search. Third is the hashing. Okay? Yeah. Linear search, efficiency category, bigger of n. Binary search, we know, bigger of log base 2 of n. Log base 2 of n. Okay? Hashing, bigger of 1. That's the average. Average. Yeah, worst case, yeah, average. Okay? Worst case, if you look at the worst case, still big O of n. Okay? Yeah. But usually we do not, it's very rare we can hit that worst case. So usually we get the average case. Okay? The average case. So bigger of 1. Yeah. Here the question is, yeah, because if we compare these asymptotic notation, we know hashing is much faster than binary search, right? Yeah, hashing, yeah, is faster than the binary search. Yeah. So there, some of you may wonder, why not we just use hashing for all data, for all our auxiliary indexing files, right? Yeah. So some of you may ask a question like this. Yeah. Yeah. Actually, it's not good. Yeah. If you switch from the binary-based searching algorithm to hashing-based searching algorithm, you will lose the order information. Yeah. Because the hashing technique, it does not maintain order information. Okay? Yeah. So that's its biggest drawback. Yeah. Hashing. This technique, okay? It does not maintain the order information. Okay? Yeah. But the binary search maintains the order information. Okay? This property is very useful. Order information. That property is extremely useful. So we don't want to lose it. Okay? So if it's possible, whenever it is possible, that means the data has the total order. So our first priority, we want to use the binary search-based indexes. Binary search-based indexes. So we can preserve the order information. Yeah. Because in many applications, the order information will be very useful. Yeah. If you lose the order information, then a lot of applications, it's not convenient to use the data. Okay? So it's a big advantage. So we don't want to lose that big advantage. So we are willing our search algorithm, binary search, slightly slower than the indexing. Yeah, but yeah, actually it's, if we use our sophisticated multi-level tree structure, multi-level trees, just as I described it at the beginning of this class, multi-level tree structure. Yeah, yeah. So it's a multi-level. What kind of multi-level? Hundreds of branches. That from level to level, you expand to hundreds of branches. That's the reason you can cover a huge file. Okay, multi-level tree structures. Okay, yeah. So you can preserve the order information. Yeah. Preserve order information. And the number of comparisons, that number is not big. Okay, small number, as I said, 4 or 5 comparisons, you can cover billions of data pieces. Only 4 or 5. 4 or 5 levels, you can cover the table with billions of rows. That's good enough. Okay? That's good enough. Yeah. All right. Yeah. Yeah. Another thing, for this class, let me make some comments. Yeah. Another thing for this class, as I said, I do not plan to go very deep in this topic. Yeah, because for this class, when I taught 10-something years ago, I taught this class. At that time, I went, much deeper. Yeah, when I recall my notes at that time, I went much deeper. Yeah, because we will do a lot of computation questions, and those computation questions not easy. Not very easy. Yeah. How many times you need to go to the hard drive, to get your data? So, we need to do a lot of calculation. Yeah. Some calculation pretty complicated. Yeah. And here, recent years, especially after the, COVID time, so we reduce the, complexity. The depth of the coverage. Yeah. So we won't do the computation anymore. Yeah. Just give you the understanding of indexing technique. Yeah. So you need to do computation. Yeah. Okay. Yeah. So that's a big difference. A big difference. Yeah. All right. Most prevalent types of index. Yeah. So that's the binary search based. Yeah. So that's the 80%. Then, yes, here, tree data structures. Yeah. When we order data single level, that's not good. Because if you use the single level tree data structure, that corresponds to the multi-level. Okay? Yeah, because when you have a tree, you have multi-level. Single level, when you do binary tree directly, so you do not organize in a tree, you just, organize in an array. It's a line. Yeah, array is a line, right? Line structure. So when you use the line structure, order the data stored in a line structure, you can apply the binary search, right? Yeah. Because if you use the line structure, think about when you have billions of data pieces, how many comparisons you need to do, right? 1 billion, okay? Yeah. That number could be relatively big. Yeah. That number could be relatively big. Yeah. Okay? It may not be too big. Yeah. For example, 1 million. Yeah, let's say 1,000 corresponds to binary search 10 accesses, right? 10 comparisons. 1,000 rows, 1,000 data pieces, you need to do 10 comparisons. Yeah. 1 million is 6. Then you need to do 20 comparisons, right? Yeah. Double. Yeah. And 1 billion, 10 to the 9th, then you need to do 30 comparisons, right? Yeah. So that number is not that huge, 10, 20, 30, but think about those 20, 30 comparisons, you need to go to hard disk. Each comparison, you need to do a hard drive visits. This many hard drive visits. That could be slow, right? Think about it. You have 30 hard drive visits. Is that slow? No. So too many hard drive visits. Okay? Yeah. So definitely you want to cut that 30 number of hard drive visits to 4 or 5 visits, right? Yeah. 4 or 5, you can already cover billions of data items. Yeah. Usually, most of the time, you don't have billions of data pieces, right? There, 2 or 3 is enough. Okay? 2 or 3 hard drive visits. That's a small number. 2 or 3 hard disk visits. Yeah. So that's really fast, right? Yeah. So here you can see the tree data structure, multi-level tree data structure. That can make you data search very fast. Yeah. All right, multi-level indices. Dynamic structure, another important, yeah. So we just have 5 minutes before the class ends. Yeah. So let me talk about this dynamic structure a little bit. Yeah. Because your table, the data in your table keeps changing, right? Yeah. So it's dynamic. It's not fixed. It's dynamic. Yeah. You keep acquiring new data items, right? So your business, you keep adding new data items into your table. And you keep update your table. Yeah. And sometimes you need to delete a few items. Okay? Yeah. Think about your tree structure. How do you maintain that special tree data structure after those insertion, update, deletion operation? You maintain that sophisticated multi-level tree structure. Yeah. So the algorithm is very complicated. Yeah. In this class, we will not go there. Yeah. I remember before, I used PowerPoint diagrams to show you how to change the data structure. Okay? I will use some simple examples. Yeah. Yeah. So when you add data, new data pieces, so your multi-level tree structure needs to be changed dynamically, okay? Dynamically. Yeah. When you reduce the data inside that table, so your multi-level tree structure also need to be changed dynamically. Yeah. So very complicated, but very interesting. Yeah. Very complicated. Yeah. Yeah. For this class, we will not go that deep. We will not go that deep. Yeah. If it's possible, later I may want to see if I can, go back to the same level before the COVID time. Yeah. Yeah. Here it's hard. It's hard to recover, the depth we covered before the COVID time. Yeah. Yeah. A lot of factors. Lot of factors cause the problem. Oh. All right. Let me finish this slide before the end of this class. Yeah. So then the hashing. Option. Hashing format, no order information maintained for your table. Yeah. So that's a big drawback. That's a big drawback. No order information maintained. Yeah. So for this big drawback, this drawback is too big, so we cannot ignore it. Okay? For this reason, whenever your table for one particular column, if you have the total order for the data, then you should use the multi-level tree structure. Yeah. And you can run binary search for that data structure. Okay? Yeah. So that's your higher first priority. Yeah. First priority. Okay? Yeah. All right. So let me just stop at the end of the slide. Yeah. Next time, yeah. So here you can see for this topic, when I explain, usually it takes me a lot of time. Each slide I need to spend a lot of time to explain the background knowledge. Yeah. All right, so hopefully let's complete the remaining slides in our Wednesday's class. Yeah. Yeah. All right, yeah, that's it. Yeah.